So let's look at the discrete time Fourier transform. Now we've actually covered most of the work involved in this, so a lot of it's going to be a recap. So we start off with a discrete function of time, f of nt. So this is our f of nt here, and you can see I've chosen this one in particular as an even function. Now whenever we take this function of time and we multiply it by our e to the I omega t, now we note here that the surface e to the I omega t, it's actually e to the I omega nt because the t now is going to be discrete. But because this is an even function, it means that the sine part of this disappears and we're only left with the cosine part. So we've only drawn out the cosine surface here. So this is actually the cos I omega nt, and you can see here it's actually discrete in terms of time. So this is our time axis here. In the time axis there's only discrete values exist, but you can see in the frequency axis is still continuous, but the time axis is discrete. So in order to do this discrete time Fourier transform, we take our function f of nt and it's going to modulate the surface. So this here is going to multiply the surface, and we'll see that just in the next slide. And once it's multiplied the surface, then we're just going to be left with a whole load of cosine terms, and we add the cosine terms up in terms of the time axis. So we're going to add the cosine, we're going to add all these cosine terms up in this direction here, and when we add them all up, the height of them is going to give us the actual Fourier transform here. And you can see here that the Fourier transform, importantly, is actually going to be a continuous function because the omega axis is still continuous. Now another thing to note here is that whenever this here has modulated the surface, well, this surface is going to continue on for infinity in this direction and infinity in that direction. So it means that the output here, which is the discrete time Fourier transform, is going to be continuous, but it's also going to repeat because this surface here is going to continually repeat. So for example, the cosine term here is going to drop down, come back up, and it's going to come up and down continually, and it's going to do it continually in this direction. So it means that whenever we add in this direction here, we're going to get a term in the centre here, and once this surface has repeated again, we're going to get another one of these terms. So it's going to be periodic, and it will be periodic here as well. So that means that whenever we take this Fourier, the discrete time Fourier transform of this function, in the frequency domain, it's going to give us a periodic function. And that's going to be important for when we look at the idea of aliasing. So let's look at this modulation of the surface in a little bit more detail. So this is the same function that we had above. So this function f of nt, I can see it's an even function. Now what we've done, we've actually shown the surface, which is the cos omega nt surface, and it's been modulated. You can see the actual height of the surface has changed. So rather than being a flat surface all of height 1, so like from above, you can see it's just a surface of height 1, or a continuous height. When we come down here, the surface here actually changes and it's actually modulated. So it's actually coming up like this and coming down. So this function here is modulated that surface, and whenever we add up the values of all of these modulated cosines in this direction here, we're going to get the discrete time Fourier transform. And as I said, it's going to repeat because this surface is going to repeat in this direction and also in the negative direction as well. So along the frequency axis, the surface is going to repeat because all we have is just, in this instance here, repeating cosines. Now another thing to note here is that we can rewrite the actual function and we can simplify it. So we simplify the nomenclature. So the discrete time Fourier transform, the f of nt, well, the value of t, if we normalise that to a value of 1, then we can just say that the number n will tell us the number of samples. So for example, we say here that t is normalised to 1, and we can just say that, say for example, there's 20 samples in that particular range of 1, which in effect would be 1 second. So it means that in order to define what's happening in this discrete function in the time axis, all we really need to know is this value n. So the index tells us which one of these pulses we're actually dealing with. So it means that the nt, well, the t will disappear here as well. So we'll simply be left with the discrete time Fourier transform. We'll have f of I omega equals the sum from n equals minus infinity to infinity of f of n times e to the I omega n. And this is the general kind of format that you would tend to see the discrete time Fourier transform written in. So let's look at a forward transform. We've got this function of time here, and the height here is a. We're going to multiply it with an impulse train. So this is our impulse train here, s of t. Now each of these impulses here are separated by a value of mt. So this is, m would be 1, 2, 3, 4, 5, so on and so forth. So these are all of our impulses. We multiply this with this and we'll get a sampled function here. So this is our sampled function, and I've left the envelope in just so you can see it's the same envelope as we have up here, but the envelope wouldn't actually be there, it would just be the samples. So the thing to note here as well is that this function here, although it only exists at discrete points, it's still on a continuous axis t, so this is still a continuous sampled function. So in order to go from the continuous domain to the discrete domain, we have to use our conversion factor, and that's our little conversion factor here. So finally we'll be left with a function here which is a sampled function in the discrete domain given by nt. So on the other side here we're going to look at the actual Fourier transforms of these. So the Fourier transform of this looks like a little triangle here, and we can see that it's going to be crossing over at minus L and plus L. We know the Fourier transform of an impulse train is another impulse train, so if the distance between here and here is a value of t, so that's the period t, then the distance from here to here is going to be omega s, which will be a 2 pi upon t, and the actual height of this will be 2 pi as well. So a very narrow frequency, a very narrow impulse train in the time domain will give us a wide impulse train in the frequency domain. And to take this function here, we take this function, and when we multiply in the time domain, it's the same as convolving in the frequency domain. So we take this function and we convolve it with this impulse train, and we've seen that whenever we convolve a function, with an impulse train, it's the same as taking the function and centering it at the impulse train. So this is the convolve function here. So a thing to note here is that whenever we went from this function here to this function here in the time domain, we were going from a function of a continuous variable t to a function of a discrete variable nt, and we went through this conversion factor. But you'll note that in the frequency domain here, there's no conversion from a continuous variable omega to a discrete variable omega, because the omega axis doesn't become discrete. The omega axis always remains continuous. So if we were to come down here and we were to take the Fourier equivalent, that is the frequency domain equivalent of this function here, in effect we would be doing the discrete time Fourier transform, and the discrete time Fourier transform would give us this function here, which is exactly the same as this function here. So we can ensure that by going through this conversion factor here, that the frequency domain isn't scaled by any amount, it's exactly the same, and it remains exactly the same from this point here to this point here. So let's derive the discrete time Fourier transform mathematically. So we start off with our sampler here. So this is our sampler. We've got our delta function. The samples are separated by factors of mt, so that's 1t, 2t, 3t. So t is the sampling period. And we're summing those up from n equals minus infinity to infinity. So that's our impulse train in the time domain. And we've seen that whenever we Fourier transform this impulse train into the frequency domain, we get another impulse train. But this impulse train is going to be separated by a factor of minus k omega s. So the omega s will be equal to the 2 pi upon our t. So we've seen that whenever we looked at the impulse trains. Now we're going to take this impulse train here in the time domain, and we're going to multiply it by our function f of t, and we'll be left with this function f of st. So our function is just f of t times this here. So let's have a look above and we'll see where we are with this. So we've taken this function here, we've multiplied by our impulse train, and we've got this new function down here. So we're still at this point here at the moment. And the last stage is to go from this function of a continuous variable t to a function of a discrete variable nt, and we do that from going from the continuous to the discrete through this little conversion factor. So let's continue with the mathematics. So we take our function f of t and we multiply it by our impulse train s of t, and we get our sampled function fs of t, and that's this function here. Now a thing to note here is that this f of t is a function of a continuous variable t, but it only exists at discrete points, and the discrete points are given by the impulse train, and those discrete points are going to be values mt. So it means that we can replace this t here with our value mt. So if we take this function here and we'll just rewrite it down here, and we're going to find the Fourier transform of this function. Now this function here is just a sum of impulses, and it's multiplied by this factor here, which is just an amplitude value. So we know that the sum of impulses can be written as a sum of exponentials in the frequency domain. So this is our sum of exponentials, e to the minus I omega mt in the frequency domain, and we're just multiplying it by this amplitude factor t f of mt. So this here is the Fourier transform of this impulse train here that has been modulated by the function f of t. So now we're going to do the final section here. We're going to go from the continuous time domain to the discrete time domain. So we're going to go from a function of our continuous time t to a function of a new variable nt. So now we've got our function f of mt delta nt minus mt, and we can see the Fourier transform of this here is going to be our f of mt e to the minus I omega mt. So you can see here that from this line here to this line here, we've replaced the continuous function fmt with a discrete function, and in doing so this t here has disappeared. So this line here becomes this line here via this conversion factor, and the same at the other side here. The t f of mt then becomes the discrete function f of mt. So finally this thing here is our discrete time Fourier transform, but we don't usually see it written like that. We usually don't use the value m, we'll just replace the m with our values of n. And of course we mentioned before that we don't need to use the value of t. If we assume that it's normalized to 1, then we can work out everything here via the index n. So we're left with our discrete time Fourier transform f of I omega. Now I've put a little bar over the top there to show that this is actually going to be a periodic function. It's going to be the sum from n equals minus infinity to infinity of f of n e to the minus I omega n. So now let's look at doing the inverse discrete time Fourier transform. Now we know that the inverse transform is given by this function here, but we know that we're going to be starting off with a function which is actually periodic, that is f of I omega, and I've got this little bar above that says it's periodic. Now we've seen that whenever we looked at this here, when we looked at the forward transform. The forward transform would give us a periodic function in frequency, so this would be an fi omega with a little bar over the top. Now we can take this function here and we notice that we're no longer multiplying through the surface e to the I omega t. The surface is replaced by, the t's are now replaced by the discrete surface nt, so we end up with the e to the I omega nt. And then whenever we go from the purely continuous variable t to the discrete variable f of nt, we're going to use the conversion factor. And again, here's our conversion factor here. It's going to be t f of nt equals fnt. So it means that we're going to introduce an extra factor of t in here. So we're going to end up with a t upon 2 pi. So omega s is actually 2 pi upon t. So t upon 2 pi is going to be 1 upon omega s. And also a thing to note here is that whenever we do the integration, you'll note that we're integrating here with respect to our frequency axis, which is continuous, but we only need to integrate over one of these periods. So we only need to integrate from, say, omega s upon 2 to minus omega s upon 2, or equivalently from 0 to omega s, because the surface is repeated again and again over and over, and we only need one of these periods in order to reconstitute this function of time. So finally we're left with our inverse discrete time Fourier transform is given by f of nt equals 1 upon omega s, the integral from 0 to omega s over function f of I omega e to the I omega nt by d omega. And finally, if we were to say that if the value t here was 1, so t is normalised, we would just have the e to the minus I omega n. And again, if the t is normalised here, it would be omega s upon t, which is 2 pi upon t. The t is just 1, so it would just be 1 upon 2 pi, and that omega s would just be 1 upon 2 pi. So finally, here are our two discrete time Fourier transforms. This is the forward transform, and this is the inverse transform here. So let's go ahead and we'll look at an example of the forward transform, and we'll look at it in MATLAB as well. So let's look at finding the discrete time Fourier transform of this function here. F of nt equals a to the n u of nt. Now u of nt is a unit step, so it's only going to exist for values greater than 0. And we'll restrict this to mod a is less than 1. In fact, we'll restrict it even further and say that a has to be greater than 0. So a is greater than 0 and less than 1. So we work out the discrete time Laplace transform of our function. We multiply it by e to the minus I omega nt from n equals minus infinity to infinity. But this function here is equal to 1 whenever n is greater than 0. So this is equivalent to the sum from n equals 0 to infinity of ae to the minus I omega t, and we can take our factor of n out, and this here is a geometric series, and the sum of a geometric series of this form here is given as 1 upon 1 minus x, where our x in this case is ae to the minus I omega t. So it means that the discrete time Laplace Fourier transform of an u to the nt is going to be 1 upon 1 minus ae to the minus I omega t. So let's go ahead and we'll have a look at this graphically. So this is it plotted out in MATLAB. I've done it in 3 dimensions here, so we've got the omega axis, we've got the imaginary axis and the real axis, so it is a complex function. And I've also shown the purely real axis, I've shown the purely imaginary axis, I've also shown the magnitude here and the phase. Now the magnitude looks similar to the real axis, but it's not, it's slightly different if you have a closer look at it. And the height here is given by 1 upon 1 minus a, and the height here above the line is given by 1 upon 1 plus a. Now this is our function here. Our value for t in this case is normalised to 1, and the value for a I've picked out is 0.3. So you've got access to this and you can have a look at it in MATLAB. So this is actually in MATLAB, so you can see here that we can go ahead and we can take the three-dimensional function here, and if we turn it round we can produce the purely imaginary plot, and you can produce the purely real plot by turning it to the real axis. Okay, so that gives us the real and the imaginary, and then from the real and imaginary we can generate the magnitude. So we generate magnitude by taking the real squared plus imaginary squared and taking the square root. So it is in effect like drawing a line through the centre of this here and taking the line up to the point on this curve, and we get up to the point in this curve by taking the square of the imaginary plus the square of the real, and it gives us this line up to the curve, and all those lines are just set out in a single axis here, and that's the magnitude. And also we have then the magnitude and the phase here at the bottom. So that's us finished with the Discrete-Time Fourier Transform. In the next couple of videos we're going to look at something called aliasing. Now you can see the aliasing effect starting here, but we're not actually going to show it like this, but we can get an indication. We can see that this discrete time frequency, whenever discrete time signal, whenever we find the discrete time Fourier transform of it, we said that we're going to get a repeating signal or a periodic signal. But if the bandwidth, that is the frequency bandwidth of this signal here, is large, it means that this part of the signal here is going to impinge on this part of the signal here. You can see the crossovers and so on and so forth. You get these crossovers. So that would create a degradation of this signal, and it would mean that whenever we went to do the inverse transform, we wouldn't be able to reconstruct this signal. Now you maybe can't see it quite well for here, but over the next couple of videos we're going to introduce it in terms of convolution. So we're going to get this effect of aliasing due really to two facts. And one of the facts that we've already looked at, which is that if we have an impulse train in the time domain, it will give us an impulse train in the frequency domain. And also the second fact is that whenever we multiply two functions together in the time domain, it's equivalent to convolving them in the frequency domain. So we're going to look at that over the next video, and we'll see the idea of aliasing and how we can prevent it.